Electricity, the continuous flow of charged particles under the influence of an electric field. Electricity is a useful form of energy which can be converted to other forms such as heat, light, sound, and kinetic energy. For electrical current to flow, you need to generate and maintain a voltage across a load. One way to achieve this is through electromagnetic induction. Here is how it works. If you have a loop of wire and you move a magnet towards or away from it, an electromotive force is induced in the wire and it drives a current through that wire loop. If a galvanometer is connected to the wire loop, a deflection of its needle is observed each time the magnet is moved towards the wire. When the magnet is moved away, a deflection also occurs, but in the opposite direction, because induced current will have changed its direction. This tells us that a changing magnetic field generates a voltage in a conductor. The greater the speed of the magnet, the greater the deflection. The direction of this induced current can be determined using Lenz's law, which states that induced current will flow in a direction that produces an opposition to the effect causing it. What this means in our example is that as you push the magnet in, the current will flow in a direction that causes it to repel the magnet. This is possible because the current will produce its own magnetic field around the wire loop, and that field will be in such a direction as to cause repulsion. So if a north pole is pushed in, the field created by the current is in this direction such that the north poles repel each other. From the direction of this magnetic field, the current direction can then be deduced, using either the right-hand grip rule or the corkscrew rule that we discussed in the previous video. In this case, the thumb points in the direction of the magnetic field and the other four fingers curl in the direction of the current in the loop. Thus, current here is flowing in this direction. When the magnet is pulled away, induced current produces an attractive force to oppose the pulling. This means that the magnetic field of the induced current is now in this direction, so as to produce a south pole here, which attracts the magnet. Using the right-hand grip rule, we can deduce that current is flowing in this direction. This is the basic principle behind generation of electricity by electromagnetic induction. Energy can neither be created nor destroyed. So, where is the energy producing this electricity coming from? Give it some thought, and I will provide the answer at the end of the video. In general, to induce an EMF in a conductor, you need relative motion between the conductor and the external magnetic field, meaning that you can move the coil instead of moving the magnet. This is how it's done in power generators, by rotating coils in a magnetic field. The design is similar to that of a DC motor, which we talked about in our previous video. Actually, any DC motor that uses permanent magnets can generate an EMF if it is rotated manually. You can also use a changing magnetic field to induce an EMF without any relative motion between your components. For instance, by switching on and off this switch, you generate a growing and collapsing magnetic field during the rise and fall of the current. In this case, you can think of the changing magnetic field as being equivalent to moving a bar magnet in and out of the coil. This is the working principle of a transformer. The magnitude of the induced EMF depends on a number of factors, and these are summarized in Faraday's law of electromagnetic induction. It states that induced EMF is directly proportional to the rate of change of magnetic flux through the conductor. Magnetic flux is the total magnetic field passing through a given surface area and is measured in Webers. Magnetic flux is calculated using this formula, where A is the area and theta is the angle between the field vector and the normal to the surface area. B is magnetic flux density, which is a measure of how concentrated the magnetic field passing through the area is. This quantity can be measured directly for any magnetic field by using a Hall probe, and its unit is the Tesla. To increase the induced EMF, you can coil a wire loop into several turns. Now the magnetic flux is permeating through each of those turns. So for n turns on a coil, the flux will penetrate it n times, thus increasing induced EMF by N. Let us have an example of how to apply this law. Consider the following setup. We have a rectangular metal wire with one side that can be moved along these rails. The system is placed in a uniform magnetic field going into the plane of the screen. If the wire is pulled to the right, what is the induced EMF in the loop? Using Faraday's law, we first calculate the magnetic flux through the loop. A is the area of the wire loop in the field, and the area is perpendicular to the magnetic field. Thus, magnetic flux is this. Substituting this for magnetic flux in the equation for the EMF, we obtain this as our EMF. Length x changes as the bar moves along, and the rate of this change is the velocity of the bar, meaning that the induced EMF simplifies to BLV and is measured in volts. Induced current in the loop is then obtained using Ohm's law. As the current flows in the wire, a Lorentz force acts on it in the opposite direction, according to Lenz's law. Thus, work is being done against this force when pulling the wire to the right. This work is what gets converted to electrical energy generated in the wire loop. The direction of induced current in the bar can be determined using Fleming's right-hand rule. Shape your right hand into this symbol and have each finger pointing in the right direction. Automatically, the middle finger will point in the direction of induced current. We shall discuss the applications of electromagnetic induction in future videos, so hit that subscribe button and activate the bell icon so that you won't miss any of them. If you enjoyed the video, please share, like, and comment down below. That's it for how electromagnetic induction works. Thank you for watching.